Hello, everyone. Welcome to the Data Parallel Essentials for Python, bringing oneAPI to Python workshop. My name is Praveen Kundurti, and I'm one of the developer evangelists at Intel. Along with me is my colleague, Bob Cheeseborough, he'll be monitoring the Q&A chat and addressing the Q&A. With that, let me start and let me do the agenda first. So what we'll be doing is we'll just talk briefly on overview of oneAPI. We'll talk briefly on the Intel oneAPI AI Analytics Toolkit. We'll introduce to the Numba data parallel extension, which is called Numba-dppy. We'll also introduce to a module called data parallel control, which is DPCtl. We'll see how we can offload to a device using Dpctl. We'll go through some of the decorators that we use in this course called ngit decorator and the kernel decorator for parallel programming. And we'll try to do some hands-on either on the Intel Dev Cloud or jlsc platform. The time permits, right? So let's talk about oneAPI, right? So let's talk about these programming challenges in the current world. It is recognized today that each kind of data-centric hardware typically needs to be programmed uniquely, right? So there are different languages supporting different hardwares, and they're all unique, and right, it requires maintaining a whole bunch of different code bases and libraries. And with this inconsistent tool support, it actually cause developers to have to learn a whole bunch of different paradigms or programming languages. They may be stronger in some and may not be in others, right? It's just a challenge. So this means, developing software for each hardware platform requires a separate investment with a little ability to reuse that work to target to different hardware architectures, right? With that, we saw the challenge, and the solution is oneAPI. And the goal of this oneAPI project is to deliver a unified software development environment across CPUs, GPUs, and other different type of accelerator architectures. oneAPI is an industry initiative. What you will see today are Intel's implementation of the industry initiative, but it's very much an open industry initiative. So the goal is mentioned is to deliver a unified language and set of libraries that provide full native code performance. And we want this code performance across different hardware accelerators like CPUs, GPUs, FPGAs, and any other AI accelerators that may come into existence in the future. So oneAPI is a foundational programming stack, and it's used to optimize the middleware and frameworks that sits on top of it, including multiple AI frameworks like TensorFlow, PyTorch, scikit-learn extensions, and stuff. So that's a brief introduction of oneAPI, and let's see what's inside the Intel oneAPI AI Analytics Toolkit. So oneAPI comes with a whole set of toolkits like oneAPI based toolkit, Intel oneAPI AI Analytics Toolkit, and there is a IoT toolkit. People are interested in rendering. There's a rendering toolkit. So this oneAPI AI Analytics Toolkit, right? So with the growth of this AI, machine learning, and data-centric applications, the industry needs a programming model that allows developers to take advantage of rapid innovation in processor architectures, right? So if you see, one example is the TensorFlow that supports industry initiative and based on open specification APIs. TensorFlow uses oneAPI today on Xeon processors, and we look forward to using oneAPI to run on the future Intel architectures. Similarly, for Intel optimization for PyTorch, currently it runs on Xeon processors, but we look forward to using the future on the Intel architectures. So we got optimized versions in the machine learning space. We got optimized versions of Intel-enabled scikit-learn with a wide variety of machine learning algorithms like k-means, dbscan. Sorry, I see. I mean, there's a laser pointer that's been moving.
Yeah, I see the laser pointer.
Yep. All right. Thanks. So sorry to get interrupted, but yeah, so we got optimized versions of Intel-enabled scikit-learn with wide variety of machine learning algorithms like k-means, dbscan, SVM support vector machines, and so we got these all these extensions currently offloaded to a GPU. In addition, we got this Intel optimized XGBoost, and if you come to the top down, we got with the Intel distribution of Python, the core Python Intel distribution of Python, we got NumPy that are based on oneMKL under the hood for mathematical computations, and SciPy. These are all optimized for Intel with Intel distribution of Python. And the Numba-dppy is actually the topic we are talking about today, which can access using low-level hardware capabilities. And this is the software stack with the analytics toolkit. So if you see, we can find accelerated to end-to-end AI and data science pipelines, right, to achieve the drop-in acceleration with optimized Python tools built for oneAPI libraries, something especially like oneMKL, oneDNN, oneCCL, oneDAL, and more. We also, we can also achieve high performance deep learning training and inference with Intel optimized TensorFlow and PyTorch versions with low level optimization support for FP16, FP int 8 and floating point 16. And we also got increased machine learning model accuracies and performance with algorithms in scikit-learn and XGBoost optimized for Intel architectures. And it supports cross-architecture development across Intel CPUs, GPUs, and other compute. So just to introduce to the development sandbox. So we talked about this AI multiple toolkits, right? AI Analytics Toolkit, the oneAPI based toolkit. So to get started, the easiest way is you can create an account in devcloud.intel.com oneAPI. It just takes a couple of 2 to 3 minutes to get registered, and it's a development sandbox. Everything installed, inbuilt. Just you can log in through SSH or the Jupyter or live through the Jupyter Notebooks, and you can just get started. You'll get a 120 days of free access to DevCloud, and then I think you can go, you can extend it based upon if you got an interesting project going on. So the main advantage is right, as mentioned, all software installed, oneAPI software installed, and you got these different compute nodes with GPUs, Intel CPUs, Intel GPUs, and FPGAs that you can actually directly offload your work to. And I'll be showing when I'm doing the little bit live demo, I'll be also walking you through the DevCloud platform, and I'll show you how it works. But the main takeaway from this slide is please register to Intel DevCloud if you want to get started immediately without any pre-installation. No installation, no hardware required, just get started. So with that, let's start on the data essentials, data parallel essentials for Python. So this is a standalone extension to the numba.jit compiler that adds SYCL programming capabilities to Numba. And it's packaged as part of the Intel development of Python that comes with AI Analytics Toolkit. and also oneAPI based toolkit. So Intel distribution of Python comes both with AI Analytics Toolkit and oneAPI based toolkit. And you don't need to install any specific conda packages. It ensures, right, we have ecosystem based on SYCL. SYCL is nothing but SYCL is a heterogeneous and it provides you with basics of heterogeneous programming and the parallel programming capabilities. So what we're bringing is for the Python programmers to get benefit from XPU technologies without ruining the ecosystem, right? So we are using the Numba compiler to write SYCL programming using kernels directly from Python code and offloading to devices. And we want to take advantage of the data parallelism by this offload. And also there are further advantages like using the device memory to optimize, to ensure memory coherency overloads across host and device. And we'll go through that layer, which is called Dpctl layer. Right. And this is called a Dpctl. It provides a lightweight Python wrapper over a subset of SYCL API. And we can see, we can use different layers using, we can how you can select a device using DPCtl, right? And so actually there are 4 main modules in this. If you see, the Dpctl module was this Dpctl module was wrapper for SYCL classes, and the Dpctl memory, it wraps the unified shared memory allocators. So unified shared memory is a concept in SYCL. It's a memory-based, pointer-based memory handling approach, how you can transfer the data from host to device. And so Dpctl memory wraps these USM allocators. Dpctl program wraps the SYCL kernels and kernel bundles. Dpctl tensor is an array library complying to Python API spec, and all modules, provide this Python and Python level headers to enable their usage. In if you're writing C++ code, they got all these binders to write in C++ code. So we'll go in much detail into the Dpctl in the upcoming slides, but the main features that are provided by Dpctl are, as I mentioned, Python wrapper classes, specific to how you're actually, how you're interacting with your hardware, like platform, how you're interacting with the devices, the device selectors, how you're creating a queue and stuff. So this is the module that we use to interact with the hardware. And Dpctl is also available as part of the oneAPI Intel distribution of Python. And once you just install oneAPI, and Dpctl is ready to be used as it comes with the Intel distribution of Python.
Praveen, there is a quick question with respect to the number of nodes that is available in the Intel Dev Cloud, and if it is a parallel system or not.
Can I look at the?
So the question is, yeah.
Yeah, and I'll continue looking unless you can answer it right away, Praveen. I'm kind of looking up. I mean, typically what this is used for is just try test, a concept. So typically what you would do is specify like 4 nodes or something like that. So I'm trying to find out what the node limit is. I'm still looking at that. But unless you know it off the top of your head, Praveen, I thought, maybe you can keep flying. And I'm trying to work on this question behind the scenes. And,
yeah, I mean, DevCloud works in such a way, that, right? So you will be in the login node and you interact with the compute nodes using Qsub mechanism, similar to how if you are aware of the jlsc approach too, we do the similar way, right? And so all these nodes can be GPU, and they can have CPUs and FPGAs. There are multiple nodes, and the number of nodes actually, there is not a set of number of nodes that is defined by DevCloud, but they will be available based upon the availability, based upon how busy the dev cloud is, right? And you can actually check with a command called PBS free nodes, and you can get the number of nodes that are free on the dev cloud. And if the question is about MPI, if you want to have multiple clusters, that's something we not tried that, because it's a cluster of nodes, that's and if you are right, if you can handle multiple nodes in your program, I think that can be possible to offload to multiple clusters and create a MPI program.
Thank you.
Hope that answers the question. So let me move to the next slide. So this is the current ecosystem of the data parallel instances for Python. It's previously we used to call it as DPPy, which is data parallel Python, but now it's all data parallel instances for Python. It is a suite of packages implementing a common programming model for XPU offloading from Python. If you see, the top down layer, which is the DPCTL, which we talked about, right? This is how you are interacting with the actual hardware levels using DPCTL, and also the Python bindings for SYCL classes and the USM allocators, right? And the tensor library and implement it, the Dpctl tensor is a implementation of tensor library based on these Python array API standards called tensors. And NumPy dpnp is a drop-in replacement, which is called dpnp for NumPy, and it's an extension for Numba to so you can actually use this dpnp as a direct replacement for the for the NumPy. And Numba-dppy is actually the extension for Numba to offload to SYCL devices, which is called Numba-dppy. So this is the actual, this is the actual extension that we're using for either writing a JIT compiler, using NumPys. We'll talk about that in the coming slides. Or there's a kernel programming approach for GPU programmers, where you can use kernel decorators to actually offload to a device. So this is a little bit flowchart of with the modules in the data parallel instance for Python. So compute follows data, right? So till now, the current versions that we are seeing, even in the current lab access, we are not using this compute follows data. This is a new model that's coming up in the upcoming sometime soon. And this compute follows data is based on the Python array API standard. And the compute data follows data programming model is a Python way to specify on what device a computational kernel executes. The programming model is based on the the notion of the way the computation is taking place on the device and where the memory was actually allocated. So all the data movement across the device or between the host and the device is to be explicitly specified by the user in this compute follows data. The usage inside a kernel of 2 arrays, actually, if you got a usage of a kernel of 2 arrays allocated on 2 different devices, which is not allowed. If you see in this example, I got a NumPy array, which is executed on the default device if I don't have any parameter here. The second box, you see, I got a NumPy array, and I'm actually, it's executed on the device as GPU. We're passing in GPU as the parameter, right? And the data is lying there itself. We're computing the data here itself. In the third example, we've seen the NumPy arrays, right? X and Y are on 2 different devices, and we are trying to compute the results, which will generate an error because arrays are on 2 different devices. In this scenario, you can't actually follow this approach of compute follows data. right? So this compute follows data actually means computation on the device where the data is placed, right? Assume we, let's actually go to this, right? And if you see, assume, let's say we placed input data for an algorithm we want to run into a GPU memory, right? So the algorithm will be run on the GPU and the resulting data will be placed into GPU as well as the input data. If it's the same example we have seen here before. So I got dp.array with, which is executed on the default device, and the same code is now executed on GPU. And if I'm trying to create two data arrays, NumPy arrays on two different devices, which provides an error. So this is a important upcoming concept that, most of these data parallel essentials for Python, the scikit-learn courses, right, they'll be moving towards this approach of compute following data. With that, I was talking about Numba before, but if you're not, just a background of what Numba is, it's just a open source NumPy aware optimizing compiler for Python. So, right, it works best when you got, if you're using NumPy arrays or functions, right? If you got lots of loops, and Numba is a good candidate for using, right? So it can compile a large subset of numerically focused Python, including NumPy functions. Also, if you know about ufuncs in NumPy, so this is a very good Numba is a very good candidate. So there are actually two types of operations that Numba can automatically parallelize. So one is implicitly data parallel regions, such as NumPy expressions, ufuncs, or NumPy reduction functions. Or there is another way you can do, which is explicitly send it to data parallel loops. And there you can call number, instead of number.range, we'll call numba.prange expression. So a key distinction between the Numba-dppy and other GPU backends is the ability to automatically offload specific data parallel sections or NumPy expressions of a numba.jit function. So this is the introduction to the device. Device represents a specific accelerator in the system, and it requires a device selector to offload it to device. Right? If you see in this example, I'm printing the device information and importing DPCtl as the library, and I'm printing the device information. And if you can see, I can select multiple devices here. Right, I got a CPU device. If I select a default device, the system selects the best available device. Or if I want to offload to select a GPU device, I can select the GPU device and print the device information. So, so this is the basics of a device class and how we can query for the device and get the information of the device using the data parallel control. And I was talking about this, right? So there are two ways using numba.jit decorator and explicitly using kernel approach using OpenCL style kernel programming. You see, I got three different ways, right? So the array style programming, I got this numba.jit, calling the numba.jit decorator, and I got this is implicitly I got a numpys here, and I'm calling a son. So right, this is called automatic offload via numba.jit. So this actually extends the Numba's existing auto parallelizer to support generating SYCL kernels from data parallel code regions. And so it requires very minimal change to the existing code. You can just try to offload an existing numba.jit decorator by just calling in within the calling within a numpy arrays and offloading to a device. The other way of doing is explicitly calling the p-range, right? And in this here, I'm actually calling the same numba.jit decorator, but I'm actually creating a for loop and I'm calling prange here. And now I'm actually, sending this into the for loop. So this is explicitly calling prange. We are actually, sending it for parallel execution on the device. This is examples of implicit and explicit. The third one is the kernel style, OpenCL kernel style programming, right? And this is actually very similar to, if you are familiar with other GPU backends like numba.CUDA or numba.rocks. So the numba.dppy kernel decorator, right? It is provided in the in this complete numba.dppy package, and similar to programming, SYCL programming, right? Or OpenCL programming. So using this decorator, we are actually accessing relatively low-level SYCL kernels that can be written directly in Python. So several advanced SYCL features such as indexing, synchronization, adding fences, memory fences, calling the atomics, right? Atomics, if you're familiar with atomics, is it's sort of a automatic vectorization inside an array or something, right? So so these atomics are provided by this numba.dppy kernel decorator. So this feature is actually intended mostly for programmers, right, who already have some SYCL and GPU programming experience, this open style kernel programming. We'll see examples of all these three. So this is the first example using the automatic njit decorator. And if you see in this example, we are importing njit and from Numba, right? And we are actually calling the numpy expressions in this, as we have seen, right? I got multiple numpys, and I'm doing multiple numpy operations, which are automatically offloaded for data parallel regions. And then we are, offloading this to a device using Dpctl layer, right? So that's how we are using this automatic offload njit decorator to send it to parallel execution on the device. The other one is explicitly sending the parallel loop, and here we are importing again njit and prange from Numba, right? And we are using njit decorator to directly detect data parallel kernels using numpy expressions. And if you see, I'm specifically calling the prange in this for loop, right? And finally, we are again using the Dpctl layer to offload this to the device. So this is using njit decorator, and we'll see the kernel approach. So kernel approach is, as I mentioned, this is like a SYCL-based GPU programming. We import Dpctl, and we put in the kernel decorator here, right? And this is a pretty common way of kernel invocation. We're creating a driver, a function called driver, and we're passing in the global size and the local size of the device. So global size is nothing but the total iteration space. So you got ABC elements, and the global, so you're passing in the global size, which is a total in the range of your data size, right? And this is the default local size. So this is very similar to the kernel programming we do in using SYCL. And let's say you got these two arrays created, right? And we just calling this driver function, which internally is invoking the kernel decorator. And so this is a simple vector addition here. If you see, it's getting the global ID, the total linearity of the element, and then just adding vector of A of B with adding adding A and B in, and adding to C, right? It's a simple vector addition using the kernel programming approach. So we have seen these three different ways of sending a parallel execution, right? We'll see a little bit more in-depth examples of using simple other algorithms like Pairwise. And if you know Pairwise, it's a very, it's a famous algorithm. It takes a set of multi-dimensional points and it computes the Euclidean distance between every pair of points, right? So in this example, we are using the kernel decorator, right? Similarly, what we talked before, we got the global ID of each point using the get global ID of 0. And this is, this is exactly the, as mentioned, right? This call is indexing functions that are the same semantics as OpenCL. So you got these two loops. One is inner loop and the outer loop, right? And we are computing the, it's like something like x2 minus x1 whole square plus y2 minus, so the total number of points. And we are computing the pairwise distance in here. And we are actually offloading this to the device. So including this in the decorator and calling it from the using the device context Dpctl layer, we are actually invoking this pairwise calculation so that this can happen in parallel on the device. So this is an example using pairwise algorithm. And sorry for a little bit, this is, the slide is a little bit filled, but the main point in this is, right, we are using this k-means algorithm using the njit decorator. We are actually importing Dpctl. So, k-means, right, it's, we're calculating each point from the cluster of, we're creating multiple clusters, center of points, and we are trying to identify and, and arrange the points as per the clusters, right? So we are calling the njit, and it determines this particular function here. It determines the Euclidean distance from the cluster center to each point, right? And again, we are calling another njit here. And in this function, now we are assigning the points to clusters, and we update the centroids after each and every computation. So finally, after no more adjustments can be made, we finally got this cluster of centers and the pointers. So I got this complete code in the GitHub, the link that we'll be showing when we actually go to the dev cloud or jlsc. Once we have the algorithm ready, we are actually now offloading this to the device, and we're calling the Dpctl again layer, and we offload this to the GPU side of things. So, the k-means is calculated on the device side. And you can observe the usage here, explicitly calling the for loop with numba.p range. This is explicit way of calling the numba.jit decorators, as we talked before. This is another simple algorithm, which is, if the Black-Scholes algorithm, this is very famous in the financial side of things, where you got this strike, stock price, and got a strike rate, and the options change, based upon the change in the strike rate, right? Like it changes in the calls and puts every time, every second, stock price changes. So this will be like millions of operations per second. And we don't need to actually go through the mathematical logic here, but at least, the main understanding is this type of calculations, we are using the njit decorator here. And if you see, I got again a p-range function that is, that's executing in parallel, right? And we got all the calculating the calls and puts with the change in the current price and the strike price of the stock option. And then, the last step, we are actually calling the device context layer to offload to a GPU. So all these things that I talked right now will be slowly moved, towards a compute follows data approach. Now, actually, we are calculating things and we are sending it to the device, right? So this will be slowly moved to, in the upcoming time, we'll be slowly moving these to the compute follows data approach, and all these samples will be changed, but most of the logic remains the same, just that the device offloading will change based upon the compute follows data approach. So with that, actually, I will, if you are got jlsc account, you can actually install and make this run on jlsc, or I got all these steps put in here, and also we'll do the simple hands-on exercises on the jlsc. Let me share my screen and so I set up my jlsc account, and I got this downloaded. So yeah, so the link I can paste it in the chat window where you can actually get hold of this material. Let me actually paste it in the chat window. So I posted the link to GitHub, and once you download, once you clone your GitHub to either the dev cloud or the jlsc, right, you can actually navigate to AI Analytics oneAPI samples, AI Analytics, and go to Jupyter and Numba-dppy training, right? So before even starting here, let me actually also help you get hands-on to the dev cloud, right? Stop the screen and let me go to the dev cloud here. So I'm sharing my dev cloud account here, and so if you see, once you create an account in dev cloud, it's pretty big. You can create an account in a couple of minutes. Once you create an account on dev cloud, click on launch Jupyter Lab, right? And once you launch the Jupyter Lab, you can see this window opened up. You can click on the plus sign, terminal. You can launch the terminal. The code is a little bit slow, but let me try it again. Anyway, so with in the interest of time, so I already downloaded my coursework here. So it's oneAPI samples. So you can just go to the once the terminal launches, you can just type in git clone and clone the repository, right? And once you clone the repository, go to AI and Analytics Toolkit, go to Jupyter, Numba.dppy essentials, and you can click on the welcome.ipynb here, right? And this actually walks you through all the different modules in here. And so the introduction module, you can ignore it. It's for basic learning exercise for people who are not acquainted with Jupyter Notebooks. But if you want, if you're not familiar with Jupyter Notebooks, you can go to module 0 and get a little bit more understanding of how you can actually interact with Jupyter Notebooks. And click on Intro to DPY, and you can actually, all the concepts that I talked are actually clearly detailed here. And you can actually run the samples directly on DevCloud. So for example, right, so it uses a Qsub mechanism that I was talking before. So all the Qs, you're on the login node. If you see this Jupyter Notebooks on the login node, but you're actually submitting this to the compute node using a Qscript. We actually created a inbuilt wrapper for the Qsub commands. And this Qscript is very basic. We are passing in Qsub command to a GPU node, and we are actually passing in the script that needs to run on the GPU device, right? And similarly, if you see here, I got my Qscript here, and I'm passing in the script that I want to run on the device side, on the GPU. So everything is wrapped. What you need to do is you just need to run and run the command. So I already ran the command because it takes some time to execute on the dev cloud, 30 seconds. So I just made sure I made the runs before, so that I'm not spending the extra time for this to send to compute node and come back. It doesn't take much time, but every run takes around 30 to 60 seconds. So for example, in this, let's start with the DPCPP, right? The motivation behind is using the number, just for number, right? So if you see, if the general example, right, a common, it's a, why we need to apply the parallelism here. So the for loop, right? And if you see in this example, we're running in serial. And so these examples actually, it's handled everything sequential and doesn't apply any parallelism to the code. Because the way this code is written, it's actually a good candidate for the Numba framework. And as mentioned, right, it uses the decorators to compile in parallel. And if I don't put any decorators here and run the code, it's taking me around 25 seconds, right? But if I actually run with adding the simple decorator, it decreases the time significantly. And if you see, it actually ran below 6 seconds, because it's also includes the compute time here. But if I ran the same on jlsc, it's almost like within 1 second. So there's, you can see a significant decrease in time based upon just by including these decorators. So this is just a motivational example of how we can handle this numba.jit decorators, right? And we already talked about the data parallel control in the slides. We talked about automatic offload approach using numba.jit, and also the kernel decorators using dppy, the dppy kernel, right? So if you see this example, numba.dppy explicit parallel for loop, and we're talking the same. This is explicitly, we are calling in a p-range function, and we are doing a simple vector addition here of 2 different numpys. And we are using the Dpctl to offload to a device. And once I run this code, it's run on the Intel graphics, Intel GPU, and we got the results computed on the device side, right? So this is using explicit for loop. And then this is a same example we provided. This is using the numpys. So this is a simple L2 distance calculation, and we're calling the numpys within the function in the non-JIT decorator, and this is sent for automatic parallel execution. So this is implicit way of handling the non-JIT decorator for sending parallel execution. And the last way we talked about using the writing the explicit kernels in using the kernel decorator, right? And this example, we got the data parallel sum. Same thing, it's adding 2 matrices, 2-dimensional, right? I'm getting the global ID and for these 2 elements. And I'm, as mentioned, I created a driver function, right? Global size declared as the size of the array that we are passing. And So this driver function is calling the kernel decorator implicitly, right, automatically. And from our main program, we are creating two NumPy, the NumPy arrays, and we are explicitly calling this driver function. So the matrix addition, we are calling it in parallel on the device side, right? And we ran the code, and let me run the code. Let me see how much time it takes. I didn't run this code before, but similar thing, right? Well, this is running. We did this simple exercise here for kernel decorator, just to get our, more hands-on experience. We created this is a matrix multiplication. We did a matrix addition before. This is matrix multiplication using the kernel decorator. And I got this global IDs. If you see this dppy gem function, which is computing the matrix multiplication, right? I'm calling from the driver function, right, with the dimensions, as mentioned, global size and the local size of this. And so I'm providing the input arrays and the output array and sending this for matrix multiplication. So the simple steps are we uncomment the first line, uncommenting the kernel decorator, which I already did, and then offloading to the device and calling the driver function that computes the matrix multiplication. And if you see my, the previous run was successfully run on the Intel graphics, and matrix multiplication example also I already pre-run the application, and we successfully ran on the device matrix multiplication. So we've seen all the different approaches, right? Numba.jit decorator using implicitly using numpys, automatic offload using p-range. The third one is parallel execution using the kernel decorators, right? So that's the main part of the DPCPP, the introduction part to the dpex, numba.dppy module. And let's also look at the other module, DP control. So I'll be actually doing that on the jlsc. So, we're aware of both the environments. Let me stop my screen. And
Praveen, we have a couple of questions.
Yes, please.
So Alfred is asking, is DPPY only works on Intel GPUs?
Currently, it only works on the Intel GPUs, and yeah.
And then Ahmedur is asking, is it possible to run multi-node, multi-GPU parallel program using Python in DevCloud or oneAPI locally?
So, sorry, can you please repeat the question?
Yes, is he asking if you can do multi-node, multi-GPU parallel program using Python in DevCloud?
Oh, actually, the multi-GPU feature is not available yet, and we're planning something in the future. But currently, DevCloud has got only Intel GPUs, and you can only target the specific GPUs that are available in the DevCloud.
Okay, thank you.
Yeah, so let me share the jlsc. I'm still on there, sorry. So this is the jlsc environment. So I set up all my Jupyter notebooks, everything, logging into jlsc and enabling the oneAPI on the jlsc, and I can actually cut and paste the link. The steps if you are interested to run it on the jlsc node. Let me paste it in the chat window. These are the steps for you to run these examples on the jlsc if you already got an account. And so this is Yeah, so this is the data panel control module, right? And I see just a time check. So how much time we got more?
We have, how much longer do you need?
15-20 minutes.
That's fine. You can go ahead.
All right, thanks. So we talked about the DP control layer, right, in the slides, and this actually clearly provides a lot more details. What are the different interfaces, APIs you use, like how to call, especially the SYCL devices, how you can create, how you can interact, get hold of a device. And let's look at example, right, of create, of how we can do a device, right? So I'm importing Dpctl, I'm printing the device information. I showed you this in part of the slides. And I'm printing the information of device specific information in here, right? So the first example is creating a default device. So I'm passing in dpctl.SYCL device or dpctl.select default device here, right? And both the things written the same. The system selects the best available device for you. And so you just run this and the system picks up whatever the device it's best that it selects, and then it prints information. Or you can actually create a specific GPU device context. So I got a GPU, create GPU device here, and I'm calling dpctl.SYCL device of GPU or dpctl.select GPU device. It's the same thing. Either you call either of these functions, you can get hold of a GPU device. The third is you're checking if GPU is present. If not, you are actually fallbacking to a CPU. There's another function you can do that. So dpctl.SYCL device, GPU and CPU. So if it's GPU is not present, then it offloads to a CPU automatically. The last one is, the custom device selection. And this is another useful thing. Let's say you got multiple GPUs available in your system, and so if you got multiple devices, and let's say you want to rate it, or you want to give the priority selection to those. I got, let's say, 3 different vendor GPUs or 2 different vendor GPUs, a CPU on my device, and I want to give ice rating to any of the specific vendor, right? Then I can create this custom device selector and give a score, and based upon the score, you allocate the particular device you want to, right? And once I run this, so let me run this on jlsc. Running on jlsc is pretty fast because actually I'm on the compute node here on the jlsc, and so because I'm on the compute node, I'm actually running it directly pretty fast. So if you see, I got this results printed. And so there is another API that you can query for queues. Queue is for work management. And you create a default queue that automatically creates a device, calls the default device and creates a queue. And this queue is used for work management, right? And the other example is you can use from the filter selection, right? You can create properties called in order or enable profiling. In order queues are, it's a little bit more advanced topic in the SYCL programming, USM programming, right? You got multiple kernels that you are submitting, multiple works you are submitting to device, and the data, let's say we got common data accessing across different kernels, right? And there is a data dependency between kernels, and one kernel has to wait for the other kernel to finish, right? So there is a data dependency, and how this can be handled automatically is you create an in-order queue and you submit that, right? And this data dependencies are automatically handled, and these queues will automatically wait until the other task complete if it's dependent on the other kernel to finish for the data, so that there's no data race conditions. So this in-order queue is a important thing when you're actually trying to have this data synchronization between multiple kernels. And profiling, if you want more profiling application, you can create these queues and create a SYCL queue and and print the device information. Or you can actually specify a from a device, right? So I'm creating a CPU device here, or a GPU, I can call Dpctl SYCL device of GPU, and you know, you can create a device from that same layer. Subdevices, if you want to partition your CPU to 4 layers, right? 0, 1, 2, 3, 4, and just you want to use, let's say, part 1 and use the other 3 for different purposes. You can partition it and just use part of the partition to offload your work. And once you run the code, you can actually print the information and, you know. Right. So unified shared memory is a concept in SYCL programming world, and so it's nothing but it's a pointer-based approach that most of the C and C++ programmers are familiar. It's if you know using of malloc data, and it actually simplifies in the SYCL side of things. It simplifies programming. It reduces verbosity, and you know. If you see a simple view of USM here, right? It's host memory and GPU memory. If you see these 2 different memories, but from the USM shared memory, right? If you create a unified shared memory object, this will be accessed across both CPU and GPU the same. So this can be viewable from both the either from the host or the device. So let's look at some of the examples here, right? I got your memory USM device or memory USM host or memory USM shared. So memory USM, if I create a memory USM device object, this is not accessible on the host, but accessible on the device. A common way of doing things is creating a memory USM shared object, which can be actually accessed both from the host and the device. You just create a USM memory object, send it to the device, modify your code, and send it back to the host, and you can directly access the same data item on the host side. So this is other way of doing things, right? And I got a simple example here that you know that gives an example how you can use that USM shared device. And so in this example, right, I got MS is a USM shared object, MD is a USM shared device, USM device object, right? So this is only available on the device, but this object is available both on host and the device. And I'm creating initially a simple host buffer with some random values, right? So the first example, I'm copying from the host to the buffer. So MD is the device buffer, right? So this is actually being copied to the USM device buffer, right? And in this, right, the same MD, we are copying to the MS, which is the shared object, which is now both accessible. So we are copying from device to this shared object, USM shared object. And what you're doing is, you know, this is a simple example. You're creating a NumPy array. And so this follows a buffer because USM, you know, in Python, you can use this buffer protocol to access this USM pointer object. So I'm just creating a buffer of MS, right, which is the shared object. And I'm actually copying it to the ND array, NumPy array X. So this array is being now accessed between the host and the device, right? So we got 3 copies. One is on the device, one is shared object. Now actually we are using that and creating a NumPy array that can be host accessible. And we are printing the views of this, and they should be the same because we're generating a random view. And if you see the view is of the generated host buffer, right? Once we copy it back to the host, the same buffer we copied, so they're all the same. So these are basic concepts of memory management in using USM. And so just in the interest of time, let me actually also run through another example, which is pairwise. So let's also look at this, right? We got, you know, so this is another pairwise algorithm. And if you see here, we are calculating the Euclidean distance between multiple points, right? And let's see how we are handling the pairwise distance here, right? So I created a XBuff. We initialize the values X and Y here, which has NumPy. X is the NumPy array. D is the distance, pairwise distance, right? X is the number of points, or the points, the total number of points. And we're passing in the buffer unified as a unified shared memory, the size of the buffer and the item size, right? So we're creating X buffer, and using the concept of the buffer copy, right? We're creating an ND array and copying all the contents from X to the ND array. Similarly, this is the distance buffer. We're creating a DPCTL memory USM shared object of that. And then we're creating another ND array, copying the contents from the NumPy D to the ND array here, right? So now these are unified shared memory objects, right? And now we are passing in the pairwise distance to the pairwise distance algorithm, right? And what we are doing is the same thing. We're calling the dppy kernel, and we're getting the global ID of that, right? And we are doing the pairwise distance calculation like what we've seen before, right? And we got the D matrix here, right? And finally, what we are doing is we are copying the ND array back to X and the distance matrix back to D. And we run this calculating the pairwise distance here, and it shows the total number of time it takes to calculate the pairwise distance. So this is an example of using the USM shared memory, using DP control, and doing a simple pairwise algorithm. So we've seen the pairwise algorithm. Let me actually walk you through one more basic example, which is k-means. This is module 5. And so in this k-means, right? So we got multiple ways of, this notebook has multiple ways of implementing the k-means, first on CPU or the GPU, right? So let's go to this GPU implementation of k-means targeting GPU using numba.jit, right? So in this example, the first one is, first the output, let's see the output, right? So the size increments, so let's say we got steps of 1, 2, 3, 4, 5. So I got 5 steps in this. My algorithm is detecting in such a way that, so each step increases the size. So the second step is 2048, third step is 4096. Fifth step is 8192 size of points, the number of points, right? The number of points in the complete iteration space that we are computing, trying to calculate the cluster, assign the points to the clusters, right? So the first thing, right? We're calling, the first thing is we are determining the Euclidean distance from cluster center to each point, and observe the calling for using the prange function, right? And we're calling in the so that we are using the numba.jit and prange to calculate the Euclidean distance from cluster center to each pointer in the first step. And then the second is we are assigning the points to the cluster, and same thing we are using the prange function again here. Now each point is being assigned to the cluster of of each cluster centroid, right? And once it happens in a loop, and once the centroids are being updated, and once the positions are being adjusted, so this goes in iteration until there can be no more adjustment made, right? All these points are adjusted, and we actually clustered as per the centroid position, right? And if you see, we are calling the ng decorators and using prange, which is explicitly, and then we are finally calling this function using the device DPCTL layer. We are calling this group by cluster function and centroid function. So all these 3 functions, right? so that we are calling them in parallel, and we are adjusting the position of these centroids. And finally, right, you also got a mechanism, using atomics. Atomics, if you're aware of atomics, it's actually the way that can be, using the the SYCL way of, you can call the SYCL way of handling things here. And we are plotting the GPU results. So we ran the same code, and we can view the results here, right? If you run the code, so if you see multiple points are finally run, and all these points are clustered based upon the centroid position, and we noted them in different colors, donating different colors here. So this is a very good example that you can look around to see, the kernel-based approach and the ngit ways of handling things. So there are multiple other algorithms you can look in your free time. There is a calculation of G pairs and Black-Scholes. Pairwise we already covered, but there is much more details in that. So but you can actually go through the different algorithms and run the samples and get more hands-on experience. So with that, let me share my last slide, and we can wrap up the session, and we are open for any questions if you got any. Let me share again. All right, so we did the hands-on coding on Intel jlsc, and so the summary, right? We saw how we can oneAPI can solve the challenges of programming in a heterogeneous world. We looked at the data parallel essentials for Python layers and data parallel control module. We performed a code walkthrough of a pairwise algorithm and k-means algorithm in the Jupyter Notebooks, and did some hands-on exercises. Thank you very much for attending the session, and we are open for any Q&A